So now let's go to the very important topic, eigenvalue and eigenvectors. This is very important for our differential equations later. Let's make some definition. Let's start with the definition of the eigenvalue, eigenvectors, then translate to the ordinary differential equations. Okay, eigenvalue, eigenvector. And the eigenvalue and eigenvectors are also called the characteristic value and the characteristic vectors. You will see why that is called characteristics later. So what is the definition of eigenvalue and the eigenvectors? How they got derived for the linear algebra? So for a homogeneous equation, with n by n matrix require that the system matrix to be singular, which means the determinant of A is equals to 0. The rank of A will be smaller than m for the existence of non-trivial, or you can say non-zero, solution set of X. Okay, so for a homogeneous system, you can say Ax equals to B, and this B, so this is for a homogeneous system. In order to let this X to have some non-trivial solutions, we have to have this A part is singular, okay, is singular, which means the determinant of A is 0, the rank of A will be smaller than n, okay? So how to solve eigenvalue and eigenvectors? The B is equals to lambda x, where lambda is the eigenvalues, x is the eigenvectors. So we have Ax equals to lambda x, A minus lambda I, because this is a matrices, this is a number, so you have to times the identity matrix to make the value of that 2D matrices is lambda times x equals to 0. And based on the definition that this is a homogeneous equation, right? This is a homogeneous equation where this part is equals to 0. In order to have the solution set X to have non-zero solution, you need to have this part to be 0 or singular. So the determinant of A minus lambda I has to be 0 in order to have the X is non-zero solutions. Then the eigenvalue, lambda are the root of characteristic polynomial equation. So based on this determinant, you will derive a polynomial, characteristic polynomial, and the root of lambda is your eigenvalues. And based on the eigenvalues, you can solve what is your eigenvectors. Okay, so that is the definition or how you can solve eigenvalue and eigenvectors. Let's make an example. It's very simple to solve. So let's make an example. For example, you have a matrices, 2D matrices, which A is equals to 3 minus 1, minus 1, 3. And in order to get you eigenvalues for this eigenvalue and eigenvectors for the system A, you have to have the determinant of A minus lambda I that is equals to 0, right? So what is the matrices of A minus lambda I? That is A minus lambda I. is equals to 3 minus lambda minus 1 minus 1, 3 minus lambda. Okay, that is the new matrices. And in order to make the determinant of the new matrices equals to 0, so the determinant of A minus lambda I will be equals to 0. That means this determinant will be equals to 0. So the characteristic equations will be 3 minus lambda square minus 1. So this is the characteristic poly. So this is the characteristic polynomials. And in order to get your eigenvalues, you have to solve this characteristic polynomial to get the roots of lambda. So the 3 minus lambda will be equals to plus minus 1. The lambda 1 will be equals to 2. The lambda 2 will be equals to 4. So that the determinant of A minus lambda I equals to 0. And this lambda 1 equals 2 is one of the eigenvalues of the system A. Lambda 2 equals 4 is another eigenvalues of the system A. Okay. And how we can get, so we already get these eigenvalues, which are the roots of the characteristic of polynomial. How we get the eigenvectors? Then when my lambda 1 equals to 2, so A minus lambda I will be equals to 1 minus 1 minus 1, 1. Okay? And you know that this AX equals to lambda X, right? So this AX So you know that A minus lambda I times X will be equals to 0. So A minus lambda I times X will be equals to 0. So that 1 minus 1 minus 1, 1 times X will be equals to 0. You can write as 1 minus 1 minus 1, 1 x1, x2 equals to 0. Then you can directly get what is the relationship of x1, x2. So x1 minus x2 equals to 0. The second equation gives you the same thing because the rank of this equation is just a 1, so that they are repeating. So x1 minus x2 equals to 0. Then you can make, for example, one of the eigenvector will be 1, 1. Okay. Similarly, when you lambda 2 equals to 4, then you get A minus lambda I will be equals to minus 1, minus 1, minus 1, minus 1. And you know that A minus lambda I X equals to 0, so that your minus 1, minus 1, minus 1, minus 1 times x1, x2 will be equals to 0. And you get the relationship of your x1 and x2. Since the rank of this is only 1, so that you only get one relationship, which is x1 minus x1 minus x2 equals to 0. And you can make one of the eigenvalue, eigenvector, which is 1 minus 1. Okay, so 1 minus 1. You can have many of that case, but one of the example is 1 minus 1, or you can have 2 minus 2, 3 minus 3, etc. So for this system A, that we get our eigenvalues are 2 and 4. We get our eigenvectors is 1, 1, and 1 minus 1. That is our solution. Okay. And one more thing I want to make highlight is that, so for the system A, you have 3 minus 1, minus 1, 3. This is the 2D matrices, the system. You have eigenvectors, lambda 1 equals 2, lambda 2 equals 4. This is eigenvalues. When lambda 1 equals to 2, your eigenvectors is 1, 1. Okay, x1. When you eigenvalues equals to 4, the second eigenvector is 1 minus 1. Okay, and let's draw that into the coordination. So first you have 1, 2, 3, 1, 2, 3, minus 1, minus 1, 1, 2, 3. So when you have this x1 equals 1, 1, then this ax1 will be equals to lambda x1. And you can further verify that ax1 is indeed equals to, so the ax1 is indeed equals to 2, 2, which is lambda times your x1. Okay, so this first eigenvector is 1, 1. So this direction. And as you times to the eigenvalues, it will be just go on for these directions. Okay, that is the first eigenvalues. The second eigenvalues, ax2 equals lambda 2. So this is lambda 1, this is lambda 2 x2. And that is equals to 4, negative 4. And of course, you can further verify that ax2 is indeed equals to 4 minus 4. So the second eigenvectors is 1 minus 1. So this direction, okay, this direction. As you times your lambda, it will just go on these directions. What I was trying to point out is you have this system matrices. When it operates on your vectors, eigenvectors, x1 and x2, it will just make this whole system to go on the same direction as the eigenvectors you derived. So when you operate on the eigenvector 1, then it always will be on this direction. When you operate these matrices on eigenvector of 2, it will be always go on this direction. So I want you to have some geometry image on in your head that it will be just on these directions forever when you have this system operate on your vectors. And this is important for our ODE system. For example, you will consider about the stability of your ODE system. It can be, for example, one direction is very stable. So whenever you operate the system on one of the eigenvectors, it will converge. That means it will be go closer to 0. And on the other direction, it can be explode. Then that will just go to infinity. Or, two systems are all stable, means converge to 0, then the system will be stable. If one of the direction will go explode to the infinity, then the system won't be stable anymore. So I wanted you to have some sense that the eigenvalue and the eigenvectors can be related to the stability of the ordinary differential equations. Okay.